Good morning. So for the last couple of classes, we've been discussing the biophysical model of modeling of a neuron, right? So how do you go to various parts of the neuron and model them, describe them, the dynamics mathematically? So we have begun in a way with the Hodgson-Huxley model, which talks about how the action potential is generated in the axon hillock because of voltage sensitive channels. So then for the last few classes, we have been discussing dendritic processing. So we began with steady state voltage calculation, and then we solved the temporal equation, right, and found temporal solution. So we found that for an infinite cable, right, we defined some kind of a pseudo velocity of propagation, and we showed that that velocity is proportional to square root of diameter of the cable, right. But I also mentioned yesterday that when it comes to realistic large neuron models, right, we won't be solving the equations analytically, it's not practical. So we'll just depend upon numerical simulations, and we'll have a demo on that later next week. So the next, so we have four signaling components. The next component we'll be discussing is modeling the synapse. So just a quick recap of synaptic function. So we know that at a synapse, you have an action potential traveling from the axon hillock to the presynaptic site. At presynaptic site, there's a chemical transmission of neurotransmitter, and which arrives at the postsynaptic site, acts on a receptor, and produces a postsynaptic potential. And this potential can be positive or negative, right? If it is positive, we call it an excitatory synapse, and the resulting voltage is called an excitatory postsynaptic potential. And if it is negative, that occurs at an inhibitory synapse, and the resulting voltage is an inhibitory postsynaptic potential. So we also know that when the action potential arrives at the presynaptic terminal, right, the neurotransmitter, which is packed in vesicles, so these vesicles move towards cell membrane and spill their contents into the synaptic cleft by a process called exocytosis. The neurotransmitter molecules then bind with the receptors, and then the channel opens briefly, and the current rushes in. So that's these events we are familiar. Now, when we talk about modeling a synapse, there are many aspects of it that you can model, because we have just seen how complicated the synaptic function is and how many different components there are. So when we talk about modeling synapse in this course, we'll only be talking about one aspect of it, which is how is the postsynaptic potential generated, right? So that voltage generation, how does it occur, and what is it like? That's what we'll look at. So we won't be looking at all the other presynaptic events, for example. Now, when the neurotransmitter acts on the postsynaptic terminal, or more precisely, it acts on the receptors, right, associated with some channels. And if these channels are inotropic, have inotropic receptors, the receptor and channel are part of the same protein complex. So the neurotransmitter molecule binds with the protein and just it opens the channel. So in such case, basically, the effect of the neurotransmitter or neurotransmission on the postsynaptic membrane is basically opening some channels or increasing some channel conductance, right? So if you want to model the PSP generation on the postsynaptic side, all that you have to do is write down the membrane equation for the postsynaptic side, or membrane circuit model for the postsynaptic side, and then write the equation of the voltage dynamics. In the circuit model, you just have to figure out how to incorporate these channels which are affected by the neurotransmitter. So let us look at that. So you can, so the neurotransmitter affecting a conductance is modeled by this function. G sin is the conductance, and basically the conductance briefly increases and again comes back to zero, comes back to a low value. So therefore, that is because these channels open because of neurotransmitter and then close again. So that is captured by this function, and this function looks, you can easily guess, looks like this. Sorry. Right, it rises to a peak and then falls off asymptotically to zero. So now, how do you incorporate this in a circuit model? So on the postsynaptic side, right, we can, since we assume that on the postsynaptic side, which is a dendrite, there are no voltage sensitive channels. But I'll correct this statement later on. But let us stay with it for some time. So on the post-synaptic side, there are no post-voltage sensitive channels. You have the capacitance, and then whatever channels are there, you can combine them all by Thevenin equivalent, Thevenin theorem, and calculate Thevenin equivalent. So you have simply a resistor and a battery combination, or a conductor and a battery combination. So now the channels which are affected by the neurotransmitter, let us keep it separate. Let's not mix it up with the Thevenin equivalent, because these are now time varying channels. So I cannot just mix with this. Now, so the arrow indicates that this conductance is time varying, and so this conductance we have seen in the previous slide varies in this form. So all that we have to do now is solve this circuit and see how the voltage changes, and that should give us something like the PSP. So the transmitter, which acts, the ion channel on which the transmitter acts, right, through the receptor, also has a nonce potential associated with it, and that we call ESIN. Okay, so basically the effect of the neurotransmitter on the postsynaptic membrane is coming through this branch, right, which has a conductance which is controlled by the transmitter and a battery and a nonce potential. So other things are all standard. So you have vrest, which is so suppose these channels are completely closed, so the conductance is 0. So this branch is completely cut off. So then the membrane will be at certain voltage, and that is vrest. Okay, so let us now write down the equations for this. So C dV by dt. So we know that sum of these three branch currents is equal to the input current, right? So C dV by dt plus G sin, okay, times. So what we'll do is, so we'll write this as first as in this form: G sin times Vm minus E sin plus Vm minus Vrest by R. So we're indicating this by resistor R and this by conductance G sin. So this can be written as, this is Vm. So it is C dVm by dt plus G sin times Vm minus E sin plus Vm minus Vrest by R. Okay. So okay, so now what we'll do, we'll look at, we want, since PSP is a deviation from the baseline, right? So we'll introduce a new variable called Vm minus Vrest, and then write down the equation in terms of that. So C d small v, or say let's say d nu by dt plus G sin t times V plus Vrest, so because this Vm minus C sin plus V by small v by R is equal to 0. So this again, if you take all this, we assume that there is no external current other than whatever is the current that comes through the synaptic channels, right? So we have take this to the right side and separate the terms which depend on small v and separate all other terms. You get G sin minus of G sin plus 1 by R times P plus G sin times E sin minus Vrest. Okay, so basically what's happening is this equation is kind of in this form. Okay, so this small v is like this x here, dx by dt. There's a time constant, right? And minus x plus some external input I of t. Now we know that for this simple first order system, if I of t is like a positive pulse, right, x of t will have a positive deviation. It will go up exponentially and come down exponentially. If I of t is a negative pulse, x of t will have a negative deviation, go down exponentially up to a point, and then come back up to 0. So now, how does this term look like I of t? So basically, G sin goes to a positive value, stays there for some time, and comes back to 0. I mean, simply putting it simply. So therefore, this if you call it I sin, IT, right, some kind of external input current. If this current goes to a positive value and comes back to 0, then we will take a positive deviation. If this current goes to a negative value and comes back to 0, and then we will take a negative deviation. So that it's as simple as that. So now, when will this go to positive negative? It depends on the sign of this quantity. So let us look at some cases. If E sin is greater than V rest, that's one case. E sin less than V rest, another case. E sin is equal to or almost equal to V rest, that's the third case. Let us look at the three cases. So obviously, if E sin is greater than V rest, right, you have V will be positive. You have a EPSP, right, and this happens in, for example, in fast excitatory synapses with the AMPA receptors, okay, kind of AMPA receptor, and with glutamate as a neurotransmitter, because this is a very widely occurring kind of receptor in the brain. Right at this point, you have with these kinds of synapses, you have a EPSP, and these are excitatory synapses. Similarly, when E sin is less than V rest, right, the current injected will be negative, so therefore there's a negative deviation, and you call that an IPSP. This occurs in inhibitory channels, right, which were typically certain potassium channels with GABA as a neurotransmitter and GABA B as a receptor. At this, synapses, right, you have a negative deviation V, and you have an IPSB. Now, a more interesting case occurs when E sin is roughly equal to V rest. Okay, so what happens then? In fact, so nothing should be happening, right? That is, the channels open, but nothing happens, because even though the channels open, right, when these two quantities are the same, this is zero, so there's no external current injected. All that happens is this coefficient of V, right, it briefly increases and comes back to 1 by R, right? So there will be some small blip, but no major PSP occurs, because this term, which is like external input, is zero. Okay, so it looks like a useless case, but something interesting happens. I'll tell you with this in a second. I'll tell you. So no apparent effect on the PSP, and some chloride channels, Cl minus channels, having GABA synapse with the GABA A receptor. So the synapse, the neurotransmitter at the synapse is GABA. The receptor's name is GABA A, and the corresponding channel allows chloride ions to pass. Okay, so it's a chloride channel. So this is the combination at this synapse. In such a situation, E sin and V rest are about the same. Therefore, such synapses don't seem to have any effect in isolation, but that is, by themselves, such synapses may not have any effect. But when they occur in conjunction with an excitatory synapse, then they show interesting effect. So what that means is, imagine a neuron, right, which has, so a neuron can have, so the thing is, a neuron can only release one kind of neurotransmitter, but it can receive action of many kinds of neurotransmitters. It can have many different kinds of synapses. Okay, so on the input side, there is more flexibility. So now imagine a neuron has, so these are two dendrites of a neuron. This is the axon. So imagine neuron has this kind of channel which has where V rest is equal to E sin. So we'll denote it by zero. Okay, and so I'll call this G sin 0, and the corresponding E sin 0. And similarly, there is a excitatory channel, right, where the G is GE sin. Both are synaptic channels, because there are two different synapses on the same for the same neuron, and the corresponding E will be E superscript excitatory E and sin. So now imagine if you have action potentials arriving at both these synapses about simultaneously. Right, this fellow you think will not have any effect because there's no change in current here. But if you combine the two and write the voltage equation, like what we are doing in this equation here, so this term will not have any effect. I mean, so this term will be zero, so that you can remove that, which is fine. But what will happen is, if you remove that term, right, you'll still have this will be there, right? But you will have an additional term, G0 sin, coming because of the presence of these zero channels, where oops, sorry, this should be 0. Okay, so because of this presence of this kind of channel, this kind of a synapses, right, and you have an additional term here. And because of this, the effect of this term, right, the excitatory stimulus on the voltage will be slightly lesser than what you would have without this. Okay, so because if you think of this as a constant input and then look at studies, just to give an intuitive idea, because this is not a constant input, this is a pulse. But if you think of it as a constant input, and then if you look at steady state conditions, you get G0 sin plus GE sin plus 1 by R into V is equal to GE sin times EE sin minus V res. Okay, so if you think of this as a constant, because of this term, if you do V equal to this whole thing by this, you get a slightly smaller value. So in a way, although in isolation, this channel is not able to have any effect. But when this synapse is not able to have any effect, when both kind of synapses are present, right, this seems to inhibit the effect of the excitatory channel, right? So indirectly, okay, which is a very interesting effect. So what happens is, so this kind of inhibition that is produced by the kind of channels for which the its nonce potential is equal to or roughly equal to the membrane potential, the local membrane potential, right? And that kind of inhibition is called shunting inhibition. So this is one interesting property with this third kind of channels.